Today we will learn particle size analysis by hydrometer. Introduction. Grain size distribution of soil which contain significant amount of finer particles, silt and clay cannot be done by sieve analysis. Hydrometer analysis is required to determine the grain size distribution of the finer portion. For many natural soils, we require both sieve analysis and hydrometer analysis to obtain the complete gradation of the coarse and fine fraction. In the sieve analysis test, you have used S200 sieve opening 0.074 mm as the finest sieve. Now you will perform hydrometer analysis on a fine grained soil that passes S200 sieve. According to ASTM D422, when combined analysis is required, the sample is to be divided into two parts. Sieve analysis is to be done on a coarser portion and hydrometer analysis is to be done into finer portion. Division of the sample into two portions is to be done by either of #4 4.75 mm, #10 2 mm, #40 0.425 mm or #200 0.074 mm sieve depending on the specific gravity of particles. However, for our natural soils, separation on #200 sieve will be sufficient. Determination particle diameter. Determination of particle diameter using hydrometer is based on Stokes' law, which states that the terminal velocity v of a freely falling sphere through a medium is proportional to the square of the diameter d of the particle, that is v proportional to capital D square. From this we obtained to understand the details of hydrometer analysis, it is necessary to have an idea about the apparatus hydrometer. There are two types of ASTM soil hydrometers. One is designated ASTM 151H and the other is designated ASTM 152H. The readings obtained from these two hydrometers have different meanings. Both can be used for hydrometer analysis, but calculation procedures for these two are different. Here we have described the procedure for ASTM 152H hydrometer that you will use. The hydrometer, made of glass, has a stem and a bulb. When it is inserted into a liquid, it floats or submerged in an upright position with its bulb on the downside. The stem of the hydrometer has graduation. ASTM 152H hydrometers are calibrated such that when inserted in a soil water suspension, the reading on the hydrometer stem indicates gram of soil that are in 1000 cc suspension of the density at the center of the bulb. Thus, when the hydrometer reading is 0, it indicates pure water, and when the reading is 30, it means that there are 30 grams of soil in 1000 cc soil suspension. Usually there are reading from 0 to 60 on a hydrometer stem. It can be easily conceived that as the density of suspension increases, more of the stem will come out of the suspension, and so the hydrometer reading will be increased. If we prepare a soil suspension in a jar and take hydrometer readings at different time intervals from the instant when the suspension is not disturbed by stirring or any other means, then successive hydrometer readings will decrease because particles of soil will start to fall and finally settle at bottom of the jar, resulting in reduced density of the suspension. Now, suppose at any time interval t, the distance from the center of gravity of the bulb to the surface of suspension is L. Because the location of the hydrometer bulb is related to a specific gravity of the suspension around it, L may be considered to be the distance of fall of particle in time t. Therefore, velocity of particle will be v is equal to L by t. However, when we insert the hydrometer in a soil water suspension, we do not measure L directly. Instead, if we measure the distance L1 and L2 from the CG of the bulb corresponding to two hydrometer readings R1 and R2, then we can calculate L easily for any hydrometer reading R from the equation. Here we need to notice that as we insert the hydrometer in the jar containing the soil water hydrometer bulb by half of this, that is 2V ABJ from the level where it would be if this rise have not occurred. See figure 4.1d. VB is equal to volume of the hydrometer bulb and AJ is equal to cross-sectional area of the hydrometer jar. Thus equation 1 need to be modified as Figure 4.1 Schematic diagram showing hydrometer readings and corrections. Furthermore, in the soil water suspension we can read the upper meniscus, whereas we need the reading at the lower meniscus. Then to put into equation 2, RL should be calculated as C figure 4.1c. Determination of percent finer. It has been mentioned earlier that ASTM 152H hydrometers are calibrated such that for soil of specific gravity 2.65, the hydrometer reading after an elapsed time t indicates the gram of soil in suspension at that instant. This means that if RC be the hydrometer reading, then corresponding to the diameter determined using this reading, values of A for different specific gravity of soil particles may also be obtained from table 4. The reading RC to be used in equation 5 should be obtained from the observed hydrometer reading R0 after applying the following corrections. A. Correction for meniscus CM. This correction is always additive. B. Zero correction CJ. This correction is introduced because a deflocculating agent is used in the preparation of the soil water suspension, which increases the hydrometer reading. This correction is always subtractive. C. Temperature correction CT. ASTM 152H hydrometers are calibrated at 20 degrees C. So if the test temperature is different from soil water suspension, a correction is needed. The values for temperature correction are given in table 5. Scope of the test. This test is performed to determine the percent of different particle sizes contained within a soil. The hydrometer method is used to determine the distribution of the finer particles. Apparatus. Sedimentation cylinder. Hydrometer jar bath. Dispersive agent. Sodium hexametaphosphate. NaPO3. Thermometer. Test procedure. 1. Take the fine soil from the bottom pan of the sieve set, place it into beaker, and add 125 ml of the dispersing agent, sodium hexametaphosphate 40 gram per liter solution. Stir the mixture until the soil is thoroughly wet. Let the soil soak for at least 10 minutes. 2. While the soil is soaking, add 125 ml of dispersing agent into the control cylinder and fill it with distilled water to the mark. Take the reading at the top of the meniscus formed by the hydrometer stem and the control solution. A reading less than 0 is recorded as negative correction and a reading between 0 and 60 is recorded as positive correction. This reading is called zero correction. The meniscus correction is the difference between the top of the meniscus and the level of the solution in the control jar, usually about +1. Shake the control cylinder in such a way that the contents are mixed thoroughly. Insert the hydrometer and thermometer into the control cylinder and note the zero correction and temperature respectively. 3. Transfer the soil slurry into a mixer by adding more distilled water, if necessary, until mixing cup is at least half full. Then mix the solution for a period of 2 minutes. 4. Immediately transfer the soil slurry into the empty sedimentation cylinder. Add distilled water up to the mark. 5. Cover the open end of the cylinder with a stopper and secure it with the palm of your hand. Then turn the cylinder upside down and back upright for a period of 1 minute. The cylinder should be inverted approximately 30 times during the minute. 6. Set the cylinder down and record the time. Remove the stopper from the cylinder. After an elapsed time of 1 minute and 40 seconds, very slowly and carefully insert the hydrometer for the first reading. Note, it should take about 10 seconds to insert or remove the hydrometer to minimize any disturbance, and the release of the hydrometer should be made as close to the reading depth as possible to avoid excessive bobbing. 7. The reading is taken by observing the top of the meniscus found by the suspension and the hydrometer stem. The hydrometer is removed slowly and placed back into the control cylinder. Very gently spin it in control cylinder to remove any particle that may have adhered. Figure 4.2. A. Take the zero correction and meniscus correction. B. Weight the dispersion agent and make a water agent solution. C. Take powdered soil and mix with water agent solution in a pan. D. Pour the mixture at cylinder carefully. E. Shake very carefully. F. Place the hydrometer at cylinder and take reading carefully. Combined analysis of experiment 3 and experiment 4. For mixture of coarse grained soil and fine grained soil, the following combined analysis was done. 1. Oven dry the collected disturbed sample and then break up all lumps with the grinding machine or mechanically by hammer and fingers. 2. Run a sieve analysis as above. Then wash the soil retained on the number 200 sieve. 3. Weigh out to 0.01 gram, about 50 gram of dry soil retained in pan from the sieve analysis. 4. Run a hydrometer test on the dry soil following above procedure. 5. Compute the particle size and percent finer for the two parts of the combined analysis as shown in sieve analysis and hydrometer analysis. Weight of dry soil Ws to be used in computing the sieve analysis should be the total sample. 6. The corrected percentage N is found as follows.